Hi everyone, and welcome to this session about evolutionary architecture with AWS Lambda. I'm sure I'm not the only one that found challenging evolving an application on the cloud. But more in general, it's not always easy, especially with distributed system, to grow organically an architecture. I think modularity is a key concept in architecture because it helps you to achieve the direction that the business wants to achieve. And modularity can be expressed in several layers. It could be at the code level, it could be at the infrastructure level, and it can be an architectural level. And during this talk, you will discover how modularity at the infrastructure and code level could help you to evolve easily your serverless applications. My name is Luca Mezzalira. I'm a principal solution architect at AWS. I'm an international speaker and an O'Reilly author. So today we're going to talk about a few things. So first of all, we start with the problem space. We're trying to understand why we need modularity in our code base. We then move to hexagon architecture. We understand the vocabulary behind hexagon architecture, and we analyze how it works. Then we see an implementation of AWS Lambda using hexagon architecture. And then, based on what we have learned so far, we are going to see other use cases where hexagon architecture could help to make your architecture evolutionary. And finally, we wrap up. Okay, so I believe that we all know that at the end of the day, when we start a new project, in a year time, the code base, but moreover, the whole project will be different. This is a sentence from our CTO, Werner Vogels, that explains the sentiment that we are used to discover in a hard way or not, more often than not. And it's interesting because this is the key concept of evolutionary architectures. So the fact that we create an architecture that allows us to drift towards a direction that then is used to follow the business despite they are going straight to the same direction or drifting from one to another one. Moreover, I think we are all familiar with a three-tier software architecture that is composed by a presentation layer, an application layer, and a data layer. And this is very common, especially when we start a new project or if we have a legacy project that we start several years ago. That was the reference architecture for many. But one thing that I noticed, and it wasn't just me noticing that, when we start to evolve a three-tier architecture, often there are some symptoms that makes harder to evolve this architecture. For instance, in order to quickly deploy a new feature, sometimes the presentation layer leaks inside the application layer. And the same happens with the data layer. Yeah, I know it's not the case, and definitely we're not doing on purpose. Obviously, sometimes there are forces outside our wheel that are playing this game that basically doesn't make our code base very reusable. But it's something that we need to be aware of. Another challenge that we face is when we want to move a workload to AWS Lambda. This is a direct experience. For instance, I was working in a project where we had some logic running on Amazon ECS or Amazon EC2, and we wanted to move to Lambda. At the beginning, we thought it should be pretty straightforward. The code is the same, we just need to migrate the compute layer and off you go. In reality, it was non-trivial, because the way how we structure the code, it wasn't as modular as it should be, and therefore we ended up spending weeks, if not months, for refactoring our code and start to move our logic from one compute service to another one. And I think if you are used to work with Lambdas, more often than not, you have seen this kind of codes where you start to have a bit of code that describe the Lambda handler, so the entry point of our application. And then inside the Lambda handler, you start to have information around the request that is coming in. You start to have like function like submit candidate P or candidate info, that when we start to see inside the same file what they refer to, one is referring to infrastructure, the other one is referring to the domain. And Yes, you can start thinking, but Lambda is a small construct. Yes, it's true. Is the cognitive load usually inside the Lambda is not huge, but at the same time, we need to be aware that if we work in team, it cannot be huge, the cognitive load for me, but maybe for a teammate it could be. And therefore, we really need to structure our code in a way that everyone can feel comfortable to evolve and add new functionalities or even refactor, for instance. So hexagonal architecture tries to solve all those problems. And what it is basically an application that is equally driven by programs, automated tests, and so on. The beauty of this architecture is that allows you to modularize your code not only for testing purposes, but also for allowing multiple people inside the same team to work together inside the same workload. The creation of hexagonal architecture was made by Dr. Alistair Cockburn. That is not only the creator of hexagonal architecture, but he's also he co-signed the Agile Manifesto. So he definitely shaped the industry with his invention and these ideas. And we are quite glad to discuss about this architecture today. Let's talk about hexagonal architecture anatomy. So let's see how it looks like in reality. So the first thing is the domain logic. The domain logic is encapsulating all the flux of information that needs to be computed inside an AWS Lambda in this case. Think about domain-driven design. Domain logic is just a small portion of a subdomain. And in this case, in a Lambda, it's even smaller. And it represents basically the interaction that we have to do with data and maybe then interacting with some external world that could be either a third-party service or an infrastructure. Then we have ports. And as the name suggests, ports is the only way for the domain logic to communicate externally and for the external world to communicate with the domain logic. Technically speaking, a port is an interface in typed language. But in our example, we're going to use Node.js with JavaScript, and therefore we are going to see functions. And then we have adapters. And the adapters are the anti-corruption layer for the external world. And basically is the possibility for the external world to communicate with the business logic, and an adapter will be responsible for receiving the request and then passing through the port to the business logic. At the same time, the adapter will be responsible for communicating with an infrastructure when the domain logic needs, like for instance, it has to communicate with the database. So now let's see how technically we can implement a port and adapter. So in the case of our example, here you can see a port that is nothing more than a function, because we're using JavaScript. It's not a typed language, and therefore we cannot use interfaces. But in this case, as you can see, we have a get stock data that what it does is receiving an ID and then is passing this ID to an adapter that is the one at the first line of this code. And is probably querying the database, because as you can see here is StocksDB. So that name suggests that we are going to retrieve some information from a database. If we want to see a typed language, for instance Java, as you can see here, we can use an interface for a port. And this is fine, because then it can be implemented in your adapter class for communicating with the business logic. When we go to adapters, an adapter, for instance, in this case, is wrapping all the logic of our communication with the infrastructure. So in the example before, the port was communicated with an adapter, and in this case, the adapter is using the stock ID, so the value of a stock, for communicating with the DynamoDB. And that's it. So here we can see how we wrap all the logic of integrating with the DynamoDB or the infrastructure inside the same adapter. The same could happen inside another adapter in Java. So in this case, for instance, I have an example of a Twitter client. So the Twitter client is the integration is available directly inside the adapter, but this adapter is responsible only for publishing a new tweet. And as you can see, the adapter is encapsulated strongly a specific action that is communicating with the external world, either third-party service or infrastructure in this case. Okay, so let's move forward. Apart from defining domain logic, ports, and adapters, we also need to talk about the primary and secondary actors in this architecture. So the first one is primary actors. Usually primary actors are the ones that are communicating with a Lambda function in this case. So we can be another service, maybe another Lambda, maybe an ECS machine, maybe an S3 event. It could be a front end directly. So we can have a client that is calling through an API gateway our Lambda. Or it could be a message inside the queue. So there are multiple primary actors. Everything that could trigger a Lambda de facto is a primary actor. And then we have secondary actors. Secondary actors are usually the ones that are consumed or used by our AWS Lambda. So in this case, it could be a database, like we have seen before in the example DynamoDB. It could be another service, maybe a third-party service that we need to consume in order to enrich a specific data that we are computing. Finally, it could be another message queue. Maybe we are enriching some data and then passing to another message queue. Those are some of the options. Obviously, everything that the Lambda can communicate with could be a secondary actor. So obviously, this architecture is bringing, as usual, as any architecture, there is always a trade-off, some benefits and drawbacks. So let's see the benefits. So the first thing is that the business logic is independent from the outside world. And that seems simple to understand, but trust me, is extremely powerful. It means that we can really evolve our business logic without the need of changing the all code or refactoring all the code of our application. And the same is true for adapters. Potentially, we can change an adapter in isolation atomically without the need of changing anything to the business logic. There is this concept with the hexagonal architecture of inside-out programming. Inside-out is a concept that is well described by Alistair Cockburn, and basically, instead of before having multiple layers that were communicating within each other, like in the 3-tier software architecture, inside-out means that you can start to define the business logic, and then there is a communication towards the outer part. So you start from the inside, maybe you start to run also some tests with the business logic, and then slowly but steady you build out your Lambda in this case, or your hexagonal architecture more in general, for communicating with the primary and secondary actors. Usually, hexagonal architecture makes easy to test in isolation. As we have seen, because we have ports between adapters and business logic, therefore between the business logic and the outer world, the fact that we have this isolation make it very easy to test our logic and adapters in isolation. And also, because we are structuring and modularizing our code, the technical debt tends to be very low. And that is great because it means that if we have less technical debt to take care of, we can focus our effort on creating new value and therefore adding new functionalities or improving the current functionalities inside our workload. Obviously, there are also some drawbacks. So for instance, we have to build upfront multiple layers. So we need to structure our code in a way that immediately starts to identify the business logic, the adapters, and the ports. That is not definitely a huge drawback, but it's something that we need to be aware of. The other thing is that we have loose implementation details for the business logic. To a certain extent could be also an opportunity, because if you think about that, you can structure the code inside the business logic in the way that you want. Dr. Alistair Cockburn didn't provide us a guidance on how to structure the business logic there, but definitely we can take our expertise and start to use it in order to shape the business logic in the way that we think is more optimized. So if by now you're thinking, okay, but why an hexagon? We are talking about the hexagonal architecture, but we didn't see anything that is relied on an hexagon shape. Once again, Alistair Cockburn has the answer for that. in reality, hexagonal architecture is not for the shape, but is more for the amount of sides that are available inside that shape. And that allows us to describe a complex interaction, because nowadays the world is not just linear like in a three tiers architecture. It requires more interaction. It could be automation tests, it could be mocks, it could be real traffic, and so on and so forth. So a piece of logic, or in this case a lambda function, can be triggered and can consume multiple part of the infrastructure of third-party service. So it's very important that we don't focus on the shape, but it's important also to understand why hexagon and not any other shape. Okay, so we are heading towards the demo. But before we go there, I want to visually show you what we are going to see. So the first thing that we are going to see is an example of an API. It's called the Stocks API. And we have an Amazon API gateway that is exposing an API. And every time that the client is calling this API, is triggering a Lambda. The Lambda, what it does is two things. The first thing is calling Amazon DynamoDB in order to retrieve the ID of a stock and the value related to that ID. So for instance, if there is the client that is requesting ABC as a stock ID, then the Lambda will query, retrieve and get the item of ABC, or the value or the currency for that specific stock ID. And then it's going to call a third-party service for getting real-time the currencies for translating that value in multiple currencies, because we want to show inside the interface multiple currencies available in the UI. Okay, so let's start to see how the flow would look like. Because yes, we discussed about the infrastructure, but what about the code? So the first thing that is going to happen is that there is a request that is triggering basically our Lambda. And the request will be picked up by an adapter. The adapter will pass the stock ID through the port to the business logic. Once again, the ports are there for decoupling the domain logic from the adapters, therefore the outer world from the inside world. And then domain logic, what it does is retrieving the value of the stock ID. And in order to do that, the domain logic is communicating through the port to an adapter, which is the stock ID that has to retrieve, and then the adapter will wrap all the logic for getting the data from DynamoDB. When once the domain logic retrieves this information, then is calling a third-party service that is called the currencies service. And this third-party service, what it does is providing real-time a set of currencies values that will be applied by the domain logic to the initial value, and then return all multiple currencies to the UI, because in the UI we want to show all the different values of a stock ID in multiple currencies. And once again, when the domain logic is calling the currency service, what's happening is that this passing through the port, then the adapter wraps the logic of that currency service, and when the response comes back, we return everything to the domain logic. Let's start from the end. This is what we are going to build with this API. So we want to have a GET response from an API gateway that has an ID of stock ID as a parameter, and then we return the stock ID with all the values that are already computed in multiple currencies. Let's see how we can achieve that with our hexagonal architecture approach. So first of all, I would like to take your attention on the folder structure. In this case, it's a very simple Lambda, and therefore I divided by adapters, domains, and ports my code. But obviously, you can even change it in using, let's say, a more domain-driven approach, and then identifying the different areas that is compose your application, and then create inside that folder the adapters and the ports and whatever. Let's start from the app JSON, that is the entry point of our Lambda. And here, as you can see, we don't have much code. What we have in the Lambda handler, that is the trigger from directly API gateway that we receive the request, we are going to retrieve the parameters that is in stock ID and then use that stock ID through the application. The Lambda handler in this case is just the entry point, and it doesn't do much more than that. The first thing that it does, though, is calling an adapter. Get stock request is a function inside an adapter, and with this function is retrieving the stock ID and using the stock ID to communicate what was requested by the user to the business logic. How is doing that? It's doing that through the ports. And what it means is that now, as you can see here, we have imported a port that's called HTTP handler and is passing the stock ID. Moreover, because everything is asynchronous in this implementation, when the response will come back, it will return either a result or an error to the user. Obviously, I didn't handle the error in this case. I just handled the happy path, but you get the idea. So let's go in the port. The port, because we are using JavaScript, is nothing more than a function. In other languages like TypeScript, Java, or anything that is a typed language, you will be able to use interfaces instead of functions in this case. So at the end, a port will result in an interface like we have seen in the example before. Interesting enough here, the only thing that it does, our port, is retrieving the stock ID and then passing to the business logic. As you can see, the port acts as an anti-corruption layer between the two worlds, so the adapters and the business logic. Therefore, it has to be very clear that the business logic is not going to communicate directly with the adapter and vice versa. This separation will allow us to evolve independently those two parts of our hexagonal architecture. So let's go inside the business logic now. The business logic is very simple. As you can see, the business logic doesn't have any clue on who is calling it, if he has to retrieve data from a specific database, which infrastructure is used, nothing. The thing that we have here is a bunch of currencies that we decide to use in order to translate our initial value that is in euros to US dollars, Canadian dollars, and Australian dollars. And then what the business logic does is literally business logic. So first of all, it's saying, I want from a repository to retrieve the stock value based on the ID that was passed from the port. And then is going to call a currency service, but obviously also in this case, it doesn't know which service, it just knows that it has to retrieve some currencies from an external source. And then it's preparing the response that is composed by the stock ID and the values, and then is decorating this object, this stock with currencies, adding additional currencies and apply the logic for when retrieve the currency value to retrieve the value based on the euro that was the initial one. Nothing too crazy. So let's go in and deep dive inside the interesting part here, that is other two ports that will allow us to communicate with other adapters. So in this case, we have the repository port, first of all, that is the one that is going to communicate with the database. In this case, as you can see, once again, the port is nothing more than a function. So there is no business logic. It's just needed for decoupling the two elements, business logic and adapters. So we go to the get stock value adapter. This is a function where here, finally, we start to see some infrastructure. So as you can see here, I'm using a DynamoDB, and there is all the logic for retrieving a specific ID, stock ID in this case, from a DynamoDB table. And when it's retrieved, we are passing back to the business logic. But if we go further and we start to look at the concurrency list, here we are seeing something interesting. So another port that is called get concurrency, that is calling an adapter. And this adapter has a function called get currencies. And get currencies as basically a direct straight call to a third-party API that will return real-time currencies on the currencies that we asked to retrieve. So in this case, the three that we have seen before. Now, nothing too fancy, but let's assume now that at this stage, you deploy your application up and running in your production environment, and your service start to gain a lot of traction. And therefore, you end up that you start to see throttling in your dashboard from the third-party service that is not able to cope up with the load. In this scenario, for instance, if we want to change this, if we want to let's say, change this logic, we are going to apply a cache aside pattern. A cache aside pattern basically allows us to first retrieve the data from the cache, if there is any. And if there isn't, we are going to call the third-party service, but is offloading a lot of traffic. And in order to do that, what we are going to do is, in our port, changing the adapter. And once again, you see that the function, so the API construct is exactly the same. So we are calling get currencies. So the only change that we are doing is swapping the adapter. So when we go to this adapter here, we see that instead of having a direct call to the third-party service, we are going to have an Elastic Cache cluster with Redis that is used for the cache aside pattern. And therefore, the logic that I described before, the first thing we are going to check inside our Elastic Cache cluster if there is a value called currencies. And if there is, we are going to return back to the port that we return to the business logic. If not, we are going to call the third-party service. And then here, we are going to store this response inside Elastic Cache. So if we start to, let's say, have multiple lambdas that are trying to hit Elastic Cache, probably the first one will retrieve the data from a third-party system, and then the cache will be populated. All the other lambdas will fetch directly from the cache. And also we specify an eviction time that is 20 seconds in this case. This is mainly because we want, after a certain period of time, retrieve fresh data. Obviously, it's not applicable to every single situation, but in this case, we are making that we are implementing in this way because could help us to offload a lot of traffic and be in control of the response, providing real data. In this case, as you have seen, I didn't change anything about the primary adapters. I didn't change anything about the business logic. The only thing that I had changed is at the port level. And thanks to this separation of concern between the business logic and adapters, I'm able really to evolve every single part of the application independently. Think even when we are working in a team and we have multiple developers that wants to work in the same code base. Potentially, you can have a developer that is focusing on the integration with the infrastructure, another one that is focusing on the business logic, and everything will work correctly because they can work in parallel without stepping in the toes of each other. Now, let's play another scenario. So let's assume now that this team that was working with a Lambda before going to the Lambda was working with a container. So in this case, is working with a Docker container. So what I want to show you is exactly the same example that I've just showed you in the Lambda. But in this case, and as you can see, we have adapters, we have the domains, and it's exactly the same file, copy and paste of the file. And what I have here, though, that is interesting is I have this app.json. I'm using Fastify, that is a Node.js framework for creating this API. And here I have like get stock and I retrieve the ID. And as you can see here in this let's say controller, what I have is nothing more than what I had in my Lambda handler. So
This suggests a very, very interesting scenario where potentially if I start to work with hexagonal architecture in my containers, the effort for moving to another compute platform should be meaningless, or it should be relatively small. And that's very, very important because that allows us to evolve our architecture and infrastructure in a way that would follow the business needs. And the interesting part of this is that potentially we can also decide to extract only certain part of our microservice and delegate to a Lambda function easily without the need to do a big bang refactor that we need to do for everything. We can slowly but steady evolving our workload in this way. Okay, let's go back to the slide now.
We have seen in the demo that we have additional use cases, and in the next few slides, I want to walk you through those use cases. So the first one is around testing in isolation. Thanks to hexagon architecture, we have modularized our code base very well, and therefore we can easily test in isolation our business logic from our adapters. Why would you do that? First of all, when you select a database for your workload, it's probably not going to change every week. However, when you want to introduce new functionalities in your Lambda function, probably that is going to change more often. And because you decouple very well using hexagon architecture, the business logic from the infrastructure, then you can easily create two test suites, one for the adapters and one for the business logic. In this way, when you make a change, you can on your laptop running all the tests for a specific area, and then when you go in CI/CD, you can do the full test suite for all the adapters and the business logic. This way, the feedback loop is extremely fast, your developer experience is better, and it's really easy to do that when you are developing. Another use case could be changing a trigger for a Lambda function. Imagine, for instance, the previous example. We have the API gateway that is calling directly our Lambda function. This is a synchronous interaction, obviously. Maybe you discover after a while that it's not needed and you can work with eventual consistency for that specific workload. So potentially you can have maybe an API gateway that is immediately storing inside SQS, and slowly but steady your Lambda is retrieving information and then, I don't know, elaborate them or storing in S3. It's completely up to you. But the beauty of this approach is that with hexagon architecture, in order to make this change, the only thing that you need to change is the adapter. The adapter, once again, is going to have a different payload, and therefore it just has to pass the right information to the business logic in order to maintain as it is all the logic was written inside the rest of your Lambda. Another option could be that you need to add a new trigger because your Lambda and your workload start to gain traction, and there is another part of the business that maybe requires to interact with your Lambda. And in this case, instead of having just SQS, potentially you can have another team that is using EventBridge in order to trigger your Lambda. You need to create a new adapter in this case and extract the data from the payload of the event passed through EventBridge. It's great because, once again, you're not going to change the business logic, and the only thing that you need to do is creating a small adapter that is handling this scenario. Cache-aside pattern, we have seen that in action before when we were discussing our demo. And in this case, what we have is a client request that is calling our Lambda function, and then the Lambda is normally querying our database. However, when you have a lot of traffic and the query may be repeated, you can use a cache-aside pattern, where the Lambda first is going to go through the cache and checking if there is anything available there, and if there isn't, is performing a query, and then it could store inside the cache, once again, the result of the query. In this way, you offload the traffic to your database, and you can use, for instance, Elasticache for handling your cache very efficiently inside your Lambda. From the hexagon architecture point of view, at the end, what you're going to do is changing your adapter, and once again, the rest of the application will remain as it is. When we migrate a self-managed service to a managed service, hexagon architecture it can help you. How? Imagine that you have Redis and you're using a self-managed Redis where, apart from using for as a cache, the thing that you need to do is I don't know, updating the cluster or patching and so on and so forth. And in reality, it's just time that you are wasting, and you cannot work on integrating new functionalities inside your application. Therefore, what you are thinking with your team is moving towards a managed service, like, for instance, Elasticache. So in this case, you have multiple options. First of all, you can create a new adapter and communicate directly with Elasticache. Or you can even think about implementing inside the adapter a branch by abstraction pattern, where in that case, what you have is a logic that basically is dealing with both databases and then migrates slowly but steady to the new one. So in this case, Amazon Elasticache. There are multiple options, but once again, you atomically change one part of your logic inside the Lambda, the adapter, and nothing else would change. Another pattern that you can implement easily with the hexagonal architecture is the CQRS pattern, Command Query Responsibility Segregation. Usually you use this pattern when you have and you want to split the way how one Lambda, in this case, is communicating or writing to a database and reading from a database. So in this case, you have two different options. In the hexagonal architecture, you're going to have two different adapters. However, you can think at scale even further. So you can think on having these approach with command and queries that are encapsulated inside different lambdas. So in this case, you have a lambda for reading and lambda for writing. And this approach is shining very well when you are migrating from the previous example where you have a unique lambda with multiple adapters to this one that you have multiple lambdas, because thanks to hexagonal architecture, you can extract the code very easily and you can evolve your workload following the traffic loads that you have inside your system. Let's talk about web application now. So imagine that you have a microservices application and you want to move to AWS Lambda. As we said before at the beginning of the presentation, it may not be trivial, and we need to figure out a way to do so. So working with hexagonal architecture would allow us to extract a portion of our endpoint and our API towards one or multiple lambdas. You don't have to rush and extract every single element of a microservice to one unique lambda. You can potentially refactor slowly but steady. So imagine that, for instance, you have a lot of read, but not many write, update, or deletion inside your API calls. And therefore, you can have two lambdas, one for read-only and the other one that handles all the write to the database. In this way is an intermediate step towards the final result, or maybe is enough for handling your specific needs inside your workload. I really like this approach because it allows me to slowly but steady generating value iteratively and then integrate in different stages my final architecture. Also allows me to learn if I'm doing the right steps, because I de-risk the refactor. I don't have to do massive refactor. I can atomically change small parts and then having what I need. Potentially for a certain amount of time, I can have all the reads in a Lambda and all the writes from a microservice, maybe a container that is running on ECS or EKS. Okay, so then we have another use case, that is the hybrid architecture. Sometimes you have some workloads that require to have some logic that is running on cloud, in this case AWS, and on-prem. Or maybe you want to use your workload where you have some code that is running on a Lambda, some code that is running in a container. Either case, hexagonal architecture could help you to achieve that. So we said that we have our hexagonal architecture in a Lambda, and in this case, for hybrid architecture, we can also think that we have maybe another on-prem serverless solution like Knative. Knative is, let's say, a serverless solution that is open source and allows you to run serverless your containers. And in this case, because we're using hexagonal architecture, what you can do is writing the business logic once and use in different environments, one on-prem, one on the cloud. The only thing that probably you're going to change would be the ports maybe, and the adapters for sure, because the infrastructure obviously will be different inside your on-prem environment. But as you can see, we can reuse probably the most important thing and the key differentiator for your company, that is the business logic. Those are some use cases, and I'm sure that if we spend more time together, we can come up with even more. But obviously, hexagonal architecture is very flexible and help us to achieve all of this and probably even more. Hexagonal architecture was created back in 2005. It's not a new concept of architecture. And since then, we have seen an evolution of hexagonal architecture. The one that I presented to you, it was the original one from Alistair Cockburn. But since then, we have the Onion architecture that was released for the first time in 2008. And then in 2012, we have Clean architecture. Those are based on hexagonal architecture. So when you talk about Onion architecture and Clean architecture, you know that we are talking about hexagonal architecture. The main difference, though, is how they structure the domain logic. As we said, as a drawback, the hexagonal architecture didn't prescribe the way how you were structuring your business logic. However, with Onion architecture and Clean architecture, we are going to have more constructs that will modularize even further our logic. One thing that I would like to highlight, if we're talking about hexagonal architecture inside the AWS Lambda, the fact that we have a very loose implementation for the domain logic probably could help, because we know upfront that inside the Lambda is not going to be very complex or application. It's going to be by design just a small amount of logic. And therefore, having a bit of more freedom could allow you to not over-engineering your Lambda. Therefore, my suggestion is be aware of Onion architecture and Clean architecture, and maybe in some use cases could be helpful. But try to aim for an hexagonal architecture in order to not over-engineer your code base. Finally, after this talk, probably the first question that you have and you ask yourself, is it really the definitive architecture for working with AWS Lambda? As usual, as a good architect should answer any question, it depends. It depends because your context will drive that. For instance, if you're working on a SaaS product that maybe require an evolution and you're going to work for the next foreseeable future, multiple years in front of you, probably structuring the code a bit further using hexagonal architecture could really help. Because as we have seen, it has a lot of plus, and also will allow you to scale not only your architecture, but also your team in a way that you can assign multiple domain to multiple teams. Probably if you have a project that is, or a POC that has to stand for a couple of weeks, using hexagonal architecture would be an overkill. But no matter what, try to understand, first of all, your context, and then see if this pattern could be applicable to you. So the main takeaway of this talk are the following. So we have seen hexagonal architecture. We have seen that is leveraging a strong separation of concern. We also have seen that the infrastructure is completely decoupled by the business logic, and that helps us to evolve independently and change atomically those two entities. Finally, we have seen that it's easy to test because of this modularized version of our code base. We can atomically test a portion of our logic. Moreover, we can even have a faster feedback loop when we are developing because we can run unit tests only on specific area of our application. Finally, hexagonal architecture is not great as only for unit tests, as was defined at the beginning, but is evolving your architecture and workloads. That is really, really important in nowadays in modern architecture. And hexagonal architecture can help you to achieve that. Before I left, I would like to share with you some resources. So in this link, you will find an article that I describe more in depth the example that I have shown, and also there is a GitHub repository where you can clone the repository and start to play with hexagonal architecture. That's it for me. Thank you very much. I hope that you really enjoyed this talk, and for any given reason, if you have any question or anything, you can contact me anytime.